I can never understand anything until I touch and feel it. So I'm going to take you through the whole process, leaving nothing out, of how photons will enter a camera, hit the sensor, and then the data of those values will be saved into a file, which is commonly called a raw file. And we're going to look at this data in the raw file, and we're going to try and understand what happens to it, how it reaches or becomes, a photograph or a video. Okay, so in order to do this, we're going to use a Canon 7D, which we can record RAW through Magic Lantern, which is just an amazing piece of software. And thank you, Magic Lantern, for allowing stuff like this to be possible. So I'm going to go into the menu, and then I'll move over to video mode, and I'm going to change the, I'll leave the frame rate the same, but I'm going to change the resolution to 640 because we don't want to work with a lot of pixels. It just slows down the computer. So in this way we can see, we can study each raw pixel because that's really what we want to focus on. I'm going to press the start. You can see the prepare. The red light, data light's going on. Still have to wait for, okay, we got the green light and we have recording. Okay, so I copied the MLV file, which stands for Magic Lantern Video, the raw file from the 7D into this directory. And I already have MLV files associated with MLV Raw. And you can see it's playing. I'm going to pause it. So with MLV Raw Viewer, you can set it to save as movies or DNG. If I hit the W key, I'll show you which directory I want it to go to. I've already set that. So you want to set this as DNG. It's because of that, actually, the Debaying, the stripe conversion, all this C-log, all these things don't make a difference because raw to raw, as I'm going to say many times over these videos, doesn't capture any of this information. So anyway, so I'm going to put this into the queue. So let me make sure it's writing these correctly. It is, good. And it's extracting every raw frame into a DNG frame. And you can see here is the percentage. This is great software, ML Raw Viewer, to use. Wasn't around when I first started using RAW. So anyone who starts RAW with Magic Lantern Canon, these days it's very easy. Highly recommended. Okay, so here are all the DNG files extracted from the Magic Lantern RAW video, because the video, again, is just 24 frames a second of raw data. Now, you can see thumbnails with JPEGs, but actually that's what ML Raw Viewer does. It'll create a JPEG with each frame and then save the frame's data. So don't be confused about this. The computer's not reading the raw data here. It's just actually reading this sort of thumbnail that any software that creates a DNG will usually create. Okay, so what we want to do next is we want to get the data out of one of these files. So I've written a little Python script, and you can see here I put in rawpy, the name of one of the DNGs, which I picked out from here. I picked out 230, I think. That that will have a lot of dynamic range because we want to see the again just how much data we get. So I put that file here, and then this is the CSV, and then I'll just scoot this up so you can see this over here. I already ran it, but I'll run it again. You see it opens it, process finished with code 0. That means that's good. And so if we go in here, we go to the directory I saved it in, data to CSV. Here it is. I've already opened it up as an Excel file before, so let me just open that again. And this is all the data of the raw image, of the raw frame. And this is the same data that you'll get from any camera, whether it's your cell phone or your Red Dragon, Epic Dragon, whatever. All data sensor cameras output the same 14-bit data. Okay, I have this sheet where I'm going to be able to process this data. So let me just go open up the that original file, or the file we're going to analyze. So we're doing 230, right? So I'm going to open up this in Excel. I'm just going to copy all the values here. Again, the 640 by 360 values. I'm going to paste it in this special workbook where I have a where I have some code. So I'm going to go into the code, and this is the all right, let me just move this up. This is the code right here. It's basically going to go into this sheet, and I'm just going to take you through it very sort of quickly. It's first going to go get the last column, get the last row, just so we know what the data is we're dealing with. It's going to get the minimum and the maximum, which is very important, right? We just want to look at the range of numbers from our. We don't want to, need to create colors out of data that doesn't exist, right? So if there's no data from 0 to 100, which is you can ignore it. And we put this into an array. And then this is some stuff to set up bitmaps, and just ignore it. And then here's where I'm going to do very crude debaying. So eventually, because this cell, let me see if we can find it. See, remember this thing, this pattern, this will be red, green, green. And this will be blue, green, blue, green, blue, green, blue. So we need to, for this red, we need to borrow the blue from here, and let's say a green from here, to build a full color image, full color right this pixel. And we're going to use the 3029 as the brightness of that pixel. So because it's all odd even, I just use a bunch of modular math to figure out which pixel, right? So this, if this is the red pixel, right, which on this row in this column, go get the green pixel, which is on the same row but the column next to it, and get the blue, which will be on the next row and the next column over. So it's the same thing for green, if it's green. So it just basically just goes through these things and figures out where each color is going to be. Okay, so now we say, okay, whatever the color is, let's subtract the minimum, and that's now, if it's raw, we're going to say raw here, right? We need to divide it by the range times 255 because we need to bring it down to 255. And then we're going to have the next thing, we can do a gamma. We'll go into that later. And anyway, so that's basically how this works, and creates a bitmap file. Oops, let me go change. Oh yeah, creates a bitmap file in that directory. I'm just going to call it, let's just call it our raw test, something or other. Okay, so I'm going to go up to the function that we'll call it, and I'm just going to run this. And you can see here the range is 14,260. Because it's such a high resolution image, it's basically almost using all the 14,000 bits. Is this done? It is. Okay. So now we should have a. I haven't tested this first. Well, I did it with other things, but. Let's go see if we have that bitmap in our directory. We'll go to Excel, and there's the bitmap. And the way I put it in, it's upside down. Let's just rotate this. Rotate it again. So as you can see, it's an image. I mean, this is straight from, you saw straight from the camera. This is raw data, where very crude debaying or demosaicing, however you want to call it, creates this image. And this is a true image. Now, if, actually we've, I think I had this set for using a gamma. So actually, this isn't straight from the camera in a sense, with no processing whatsoever. I had applied a gamma. So let's now instead apply no gamma. And now let's, we're going to have to close this. Now let's run it. Oops. Okay, now we've run it. So now let's go open that file. Now, again, I want to point out that this is, there we go, rotate it. I gotta fix that code. Okay, now this, straight from the census, the raw data, those numbers going straight to numbers that we can look at. And as you can see, the contrast isn't right. But this is subjective. Scientifically, you want to talk about color science, this is the truth of an image, the raw image from a sensor. However, we don't really visually find this appealing. Though again, this is factually what you're getting from the pixels of the sensor. This is without the as I probably showed you down here. This is without the gamma. Now a gamma here will basically creates an exponential curve. As you can see, it takes the gamma 1 over 2.2 and it creates a curve. Here I have another sheet. While I'm here, I might as well just go into this. So so here's a sheet. I'll probably go into this a lot later, but here you can see a gamma curve. This is the data as it is, and I made an image of it. And this is the log curve. This is the gamma I created. I moved the data around. Didn't change any data, did not add or remove data. You can actually take the log and go back to the linear data. Something a lot of people aren't quite clear about. A log data does not add or remove anything. It just changes the relationship of each dot to each other. You see in a straight line, each dot, each value is the same distance to it. If you look in here, this is a little bit closer than here. It just changes. Look here, see how wide these two dots are apart, and see how close they are here. So that's all that a logarithmic function does. Okay, now that I've taken you through the process of shooting a raw image on the camera and processing it, let's start from the beginning to really study what's going on in depth and the implications. So here's a scene of looks like a guy playing cricket, and there's the sun and there's a tree. And the way a camera works is, let's say a sunlight will go through an aperture, pass the shutter, and hit the sensor. I want to point out, right, that the aperture is variable. It controls the amount of light, that hits the sensor. So you can make the aperture small for less light or wide for wider light. The shutter also controls the amount of light that hits the sensor. But this with time, it can expose it for 1/500th of a second or for a quarter of a second for more light. The thing that people don't realize is that the sensor has a fixed pixel size. It can't change. It doesn't make a difference how much light ultimately reaches it. It can't make its pixels bigger or smaller or anything. It is what it is. And because of it, it doesn't really make a difference what you set the ISO for or anything else, because it's helpless. And you have to keep that in mind. The other thing is that it doesn't know what's bright and what's dark. Another misconception. So let's say the sun is hitting the sensor, and the sensor has a reading of 5,000, right? Well, that's pretty bright, from say 16,000 values. So, but then you go inside and you open up the aperture and the shutter and you shoot a candle, and the measurement is 10,000, right? Well, is the candle brighter? No. The sensor has no idea. The camera has no idea the absolute brightness of anything. And a lot of people confuse this. They talk about luma and lux. Yes, the amount of light has something to do with how well the sensor can read that particular set of photons, how accurate it is. But the sensor can't doesn't know what's bright or not. You do. So that's an important thing to keep in mind. And in this slide. Yes, I mean, when you take an image with your RAW file, you save what you think the ISO is, but that's just you're telling the camera that, hey, listen, I know that I'm underexposing by 2 stops, so you're going to have to amplify it later on to bring up the brightness to what I expect. And I'll save the f-stop and the shutter and the white balance, but again, these are all just your sort of notes to the file of what you want to do with it later. The camera sensor, again, it is helpless. There's nothing it can do. It just, images, but you can control the light that hits it, but it will take what it takes. So, okay. So you're behind the sensor, you write down all the values, and in, not the image I just took you through, but an image I took before, I had a minimum of 2,048, a maximum of 9,736, so I had a range of 7,688 values. So if you want to save all the values that hit the sensor, right, you need to put each value that will be anywhere from 1 to 7,688 in a little bucket, right? In a little, they call them, data bits, right? So here are how many in integer terms, in real life terms, how many values we can store in each size of computer memory. So 8 bits can store 256, right? 10 bits can store like 1,000, but we need close to 8,000, so we need 13 bits. Well, computers work best in chunks of 8, long story why, but so it's either going to need to be 8-bit or 16-bit. So we'd really need 16 bits of information, or 2 bytes, to store each pixel value to get everything included in it. Here we are back at the data, our raw data from that we captured from the camera. And let's look at these numbers. So let's just look at the first number, the top left of the image, 5,283. What does that number mean? Does it mean anything? You might say, yes, it means that's how bright the light was. And as I pointed out, however, we don't know whether that's a candle or a sun. So what really does this number say? You know what it says? Nothing. Not a thing. It doesn't make a difference whether this number is 0, 1, 5,000, or 16,000. The actual pixel values are completely meaningless. And this is something that one really needs to wrap their head around. The real value of this number is the value that it is compared to another. When we see, if all these numbers were the same, right, then we could either say it's all white or all black. An image is not an actual brightness. What it is a difference in brightness. An image is contrast. Without it, there is no image. It's either all white or all black. This number means nothing. But this number, so if we take this number, let's say when we subtract it from this number, okay, so this 2,132 is an implied number of these two numbers. And in all image processing, this is the actual number you're working with, not any of these absolute numbers, because again, they're meaningless by themselves. They're only meaningful when you put another value next to it and you see a difference in either the color or the brightness, and that's what builds an image. So it's this number 2132. It's all the implied differences of each value. Dynamic range is the difference between these two values. It is not that this value would be small or this value might be large. It's the difference of the two. I'm going to start from the beginning again, because at least for me, I need to see things many different ways until it clicks in my head. All right, so with a camera, we record many values. And when these images are recorded, we got 7,688 brightness values. We need to get that into 8-bit video. So we have to convert every number from 1 to 7,688. In this particular file I took to 1,256. When you hear crushed black, that's one way it happens. This is a different image I had taken before. So here's a raw file I took, again with the 7D, and this is how fast Stone processed it. Because again, it'll look at a raw file and it'll already say, oh yeah, I know you want a gamma 2.2. Again, these are things that happen behind the scenes that people don't really understand, that how much this stuff that's going on, so they get confused and they make the wrong conclusions when they shouldn't, because this isn't natively what's going on. Okay, sorry. All right, so here's where I'm just showing the code again, where I convert these 7,000 values into a value range into 256. Here's an image where I create a bitmap from our 13-bit raw image to 8-bit raw. And as you can see, when you do a one-to-one correspondence, the image, the contrast looks off. But again, this is accurate. This is true to what the camera saw. So then what I did is I applied a gamma, log gamma, basically an exponential curve. Remember, exponential and logarithmic are sort of like arithmetic to division, right? And I'm not doing this because this is scientifically accurate. Again, people get confused. Gammas are about what just looks good to our eyes. It could be, most accepted gammas are 2.2, but it could be 2, it could be 3, it could be whatever. Everybody has a different taste on this. And this is why photography is so difficult, because, and this is why you see so much different color profiles and LUTs and all these different theories, because there is no gold standard. Everybody is just, it's one opinion against the other, and it's very anxiety producing, very nerve wracking. At least for me, definitely in real life, when I do an image, I'll do something that looks great, I show it to my wife, she's like, oh, that's ugly, you just want to quit. Okay, so moving on. Here's the image applied with an exponential curve of 2.2. It just looks better, right? It looks better than this image. Is it better? Some people might say, no, I like this image better. Maybe this needs more gamma, right? Maybe the 3.0 gamma would look better to you. We don't know. Again, these are, when you apply all all images usually have some sort of log gamma applied to them only because it looks better in real life, not because there's any scientific reason that it has to be that way. It's just the way our biology works, just the fact of human perception. One of the difficult aspects of photography is we sort of need to keep two worlds in our head at the same time, so our two opposing thoughts. There's the world of the camera sensor, what it's seeing when you take an image, and there's the world that that we need to, I don't know how to explain it, that the real life world of how many colors we can see and how we can discern it. So when you point a camera, at something, like I said, each pixel can take 16,000 values, but really the way to think about it is it can take 6,000 differences in brightness at each pixel. So it can actually come up with 4 trillion colors, but they aren't really colors because, well, we have to go into this other world, the colors we can see. So scientists have measured, and they can, put as many colors, as many of these, brightnesses, and let's say they can put a light behind like a red filter, right? And they can vary the light to a certain extent, and assuming your pupil size doesn't change, and because this is how we look at things, on our TV, a screen, a fixed pupil size, we can only discern 16 million colors, which means we can discern 256 levels of red, green, and blue. So put it another way, let's just say you create a gradient, right? I should put one up here, but you probably can think about what I'm talking about. So it goes from white to black, right? Or from white to like darkest red, right? So if you put 250 different gradients, next to each other, you can see 256. But if you put 500, you're not going to notice any difference. Every second will look the same as the one before it, right? And if you put like 100 gradients, you'll notice that they'll sort of jump. You'll get banding. So again, in the real world, in our displays and everything, we see about 256 shades of anything. After that, it doesn't make a difference. So if you look at the camera, it can see 16,000 shades, right? So, but we can't see that. So what happens in photography and video is we transform these 16,000 shades down to 256 shades. And essentially we transform, we round down to this. And that's great. And that's how we can see it. But the problem with photography is we want to go back. If we want to like do a different transformation or different rounding down because we want to pick different values from this, we cannot go back. I think that's just very important to understand that although the camera has, let's just say, a dynamic range of 12 stops, that's great. But once we transform down to our 8-bit space, we're not really in 12 stops. We're really in effectively 5 or 6 stops. These 256 levels. I'm going to have to do a different video to talk about log gammas in 8-bit video, but I just want to give a taste of, just in general, just how difficult it is for today's computers to deal with video or raw or image data. Again, the manufacturers will think, oh, you get the latest computer with the i7 Ryzen, or this 8 GB GPU memory, video card, and it can deal with the stuff easily. No, it cannot. Nobody wants to say the truth. Our computers are no match for the amount of data that the camera can basically record. They just cannot keep up with it. And to show this, I'm just going to go take it through some simple math. One frame of video is 1920 by 1080 pixels, right? That's 2 million pixels for one frame of video. There are 30 frames of video 1 second of TV. That's 62 million pixels, right? That should come from whatever video you've taken in a perfect world, right, to your display. You want to get as accurate a color as you can get. And again, we're just talking about 8-bit video here, right? We're just talking about 8 bits, 256 bits per color, 24-bit full color video. Okay, so each pixel is 24 bits of full color value, right? So 1 second of video requires 26 million values, right, times 24 bits, because we need 3 bytes to record that full color video. That means for every second, we need 1,492 megabits of throughput. Do you know that the average broadband download speed in the US, your cable, does 64 megabits per second? That means if you divide 64 divided by 1492, if you took you go out and take a video with your RAW camera and you put an 8-bit and you want to transmit to me the image just as you got, like perfectly, you could only send 4.28% of it through the internet to me. Think about it. It's incredible, right? I mean, people, all these video compressions, they throw out so much data. You just, again, do it in another video. But oh my God, I mean, I mean, we all understand it throws out a lot, but I don't know if people really understand just how much. So to make, be even more surprising to you, let me just delete that, is that Netflix compresses HD to 5 megabits. So think about this. This is how much data must be thrown out to shrink 4,492 megabits to 4 megabits, right? Think about that. Think about how much must be thrown out. So first, your computer equipment will shrink each image just like a normal single JPEG, right? There's almost so much it can shrink an image spatially. So then it basically has to say, oh, well, the next image next to it, after it, does it have the same pixels? If not, let's not repeat them. So it does all that kind of, compression. But think about it. I mean, to get from 1492 to 5 megabits, there's a lot of places where it just literally has to just throw data out, which it does. So when you see 420 data space, it's basically saying, I have 8 pixels, but I'm only going to use 2 pixels worth of color data. I'm just going to guess on the rest. Now, when images are moving quickly, you just don't notice it. So it's fine. I mean, again, biologically, we see, contrast, just raw contrast between dark and bright more than we see a color difference. So you can throw out a lot of color and we don't really notice. But again, I just want to emphasize this fact that computers can come close to processing all the visual data that they record. They can't even come close to processing all that data after we move it from its 14-bit pixel value to an 8-bit pixel value. It still has to throw out 95% of it to show you a video on Netflix or whatever, right? Okay, so hopefully this video was helpful, and hopefully, well, see if I do another.